Hello, my friends. This is Ollie, short for Olympia, and if you've ever felt a slight shiver at the words chaos theory, well, buckle up. Today, we're taking a deeper, longer dive into this mesmerizing realm. I promise, no butterfly cliches this time, at least, not in the usual sense. Let's begin with something far more mundane, and yet strangely enlightening. Picture an egg. You crack it, and the yolk spreads across the pan. You can't unscramble it. Once that orderly membrane is torn, it's done. That, in a nutshell, is entropy, a push toward disorder that can't be undone. Now let's contrast it with chaos. The idea that a tiny change in initial conditions can balloon into dramatic effects, even in what might appear to be a rigid, rule-bound system. Entropy is about a one-way street from order to disorder, while chaos is about our universe's uncanny sensitivity to the slightest nudge in starting conditions. Trust me, these two concepts get confused all the time, but they're more like cousins than identical twins. Let me illustrate with an example that's neither a dripping faucet nor a so-called butterfly. Think of weather patterns. On the one hand, we see entropy at work. Energy dissipates, storms eventually weaken, heat disperses. Yet weather is also an incredible display of chaos, where tiny temperature differentials can spawn gigantic cyclones or intense rainfall. The unpredictability of a 10-day forecast, that's chaos. This is where Edward Lorenz comes in. In the early 1960s, he was a meteorologist tinkering with a primitive computer simulation of the atmosphere. He changed a number from 1,000 to 1,001, expecting practically the same outcome. Instead, the simulated weather diverged wildly, like driving along the same road, but suddenly veering off into a different dimension. This phenomenon is called sensitive dependence on initial conditions, and it's the bedrock of chaos theory. But enough dryness. Let's get to the math. Lorenz famously used a simplified system of 3 coupled differential equations. Let me read them slowly, so 11 labs can parse them. dx by dt equals sigma times, open parenthesis, y minus x, close parenthesis. dy by dt equals x times open parenthesis, rho minus c, close parenthesis, minus y. dz by dt equals x times y minus beta times z. Here, x, y, and z might represent, say, simplified variables for temperature, velocity, or fluid flow in a convection current. Meanwhile, sigma, rho, and beta are parameters, a bit like turning knobs on a control panel. Depending on how you set these knobs, you can drastically alter the system's fate. It might settle into a tranquil cycle, or it might explode into the legendary Lorenz attractor, that swirling, figure-8 pattern that never repeats, but also never leaves a bounded region. One way to visualize these equations is like a perpetual tug-of-war. X tugs on y tugs on z reacts to x, back and forth, back and forth. Each variable's rate of change depends on the difference or product of the others, creating a feedback loop that can be surprisingly delicate. A tiny tweak to x0, or y0, or z0 might catapult you into a completely different trajectory in the long run. That's chaos, apparently deterministic, yet effectively unpredictable after some time threshold. Why do we bring up these equations in the first place? Because they show how seemingly innocent math, just 3 lines of differential expressions, can unleash infinitely complex behaviors. If the parameters cross certain thresholds, the system no longer settles into a neat state. It starts swirling in an unending dance, creating what mathematicians call a strange attractor. It's strange because it's fractal-like. No matter how deep you zoom in, you keep finding more intricacy. Now, let's link that to entropy again. If you just let your cracked egg sit, it's not suddenly going to reform into a tidy shell. That's entropy, marching onward. But if you model how, for instance, the yolk's texture interacts with heat in a swirling pan, you might see chaotic microcurrents in the fluid. That swirling is chaos, sensitive to exactly how you tilt the pan or how hot that flame is. Meanwhile, the unstoppable, you can't unscramble the egg, is entropy. They're related, but not the same. I learned to differentiate these concepts from my late professor, Sergei Leble, He used to say, "Chaos demands change in time. Your messy desk isn't chaos if it stays messy without evolving." As for the smell of perfume wafting around a room, he'd wonder what swirl patterns are formed in the air, and how a microscopic shift in airflow could change the entire trajectory of those perfume molecules. He was the one who taught me that behind all these phenomena, unpredictable weather, swirling fragrances, there are these potent, unassuming equations just waiting to be unraveled. No matter how many times you measure those initial conditions, you'll never get them perfect, and nature's chaos takes full advantage of that imperfection. Let's pivot to fractals for a moment, because fractals and chaos are close cousins. A fractal is a shape or pattern that repeats itself on smaller and smaller scales. Think of a coastline, where using a smaller ruler just reveals more jagged contours. Benoit Mandelbrot famously showed how clouds, mountains, and even the branching of blood vessels follow fractal rules. Chaos can produce fractals, and fractals can exhibit chaotic features, like infinitely nested complexity. The Lorentz attractor itself is sometimes viewed as a fractal set in three-dimensional phase space. And then there's quantum theory. It might seem distant from dripping faucets or swirling perfume, but quantum mechanics has its own brand of unpredictability. Some researchers speculate that chaotic dynamics might appear in quantum gravity proposals, especially when dealing with black holes. Because black holes not only twist space-time, but also could scramble the information falling in. Some physicists wonder if black hole horizons host chaos, akin to a Lorentz-like attractor. You see, chaos is all about how a small trigger can send a system spiraling. Black holes are about extreme gravitational spiraling. Throw in quantum uncertainty, and you've got a brew of pure, mind-bending possibilities. Are these proven? Not necessarily. But that's what makes science so exhilarating. Seeing patterns from the humble Lorentz equations, possibly echoing across cosmic scales. On a more everyday note, let's talk traffic. You inch along, then suddenly, the jam clears with no obvious culprit. Chaos. Each car's speed and position feeds into the next, compounding microscopic decisions, like braking a bit or accelerating too fast. If you tried to model that in equations, you'd find small differences in driver reactions, leading to drastically different outcomes in overall traffic flow. It's a prime example of chaos in daily life, far more tangible than electron orbits or cosmic strings. So yes, chaos is intimately real. It's hidden in your heartbeat, that slight variability that keeps you healthy. Too orderly, and your heart can't cope with stress. Too chaotic, and you risk arrhythmias. Chaos seems to be the sweet spot of adaptability. That's one reason many scientists and philosophers get excited. Chaos theory suggests the universe can be deterministic on paper, yet practically unpredictable in execution, granting us a fascinating blend of structure and spontaneity. Let's circle back to Lorentz's equations to wrap up the heavier math. When you look at dx by dt equals sigma y minus x, that basically says the rate of change in x is proportional to how different x is from y. Meanwhile, dy by dt equals x, or ho minus z minus y, tells us that y changes based on xz and a parameter called rho. And dz by dt equals xy minus beta z ties everything together, hinting that z's changes depend on x times y minus a damping term, beta z. If you imagine these as vectors pulling in different directions, you can see how one slight tweak at the start might send the entire future of x, y, and z spinning into a completely new region of the attractor. That's why we call it chaos. It's a strong illustration that simple equations can produce swirling, fractal motions that never repeat. By now, you might be wondering, how does this matter for me? Well, beyond the weather forecast, chaos theory shows up in ecology, population booms and crashes, economics, market fluctuations, neurology, brainwave patterns, you name it. Anywhere feedback loops exist, chaos can lurk in the background, shaping long-term outcomes in ways no simple formula can fully predict. And that's the crux. When chaos meets entropy, you have a system that not only evolves unpredictably, but also devolves into a less ordered state overall. That's how a hurricane can spin up from slight pressure differences, chaos, eventually dissipate, entropy, and leave behind a world that's never quite the same. Nature isn't just about random accidents or perfectly clockwork laws. It's a tapestry of fine-tuned interactions that can tip from calm into turbulence with just one tiny push. So, my friends, that's the expanded story. From a scrambled egg demonstrating irreversible disorder to Lorenz's deceptively simple equations, unveiling the swirling fractal drama of chaos. Entropy and chaos, two threads of nature's grand design, sometimes woven together, sometimes standing on their own, but always reminding us that the universe is far more flexible and inventive than we might initially believe. If you enjoyed this deeper, more prolonged look at chaos theory, let me know. There's still so much we could explore. Fractal dimensions in detail, quantum chaos near black hole horizons, partial differential equations that drive real weather simulations, or the mesmerizing world of twistors, solitons, and wavelets. You name it, and I'm thrilled to talk about it. As always, please subscribe if you found this illuminating. I feed on your suggestions, and who knows? A tiny comment from you might steer the entire future of this channel into a brand new orbit of exploration. Stay cruised, stay hyper-focused, and keep marveling at how a seemingly minor shift in perspective can unleash an avalanche of discovery. After all, that's the power and beauty of chaos.